there. Okay, so how are we this week? You've started to hit the big time now. You've got quite a lot on your plate, I notice, as I've been checking through. The fortuitous thing about this is Mary Copeland is an exemplar of teaching and learning mathematical sciences, so you've got that in your favour in a big way. So now's your best opportunity to chow down and make sure you get through your course. She's done a fantastic job assembling all of these notes and stuff. It used to be post a PDF and post a video. Now it's much more involved than that, which she's done from her postgrad work with teaching teachers. So you've got a great opportunity this semester to get through and get it all sorted out. Alright, so I thought I might just quickly do a implicit differentiation again, just to revisit that whole thing, unless you've got anything pressing. So as it heats up, you may come with a pressing question, so I'm happy to help out with that. If you're otherwise happy for me to just do it, then I'll just get on with it. Alright, so I noticed in the I'm just getting the relevant bit, week 4. So I might just open this in a new window and just pop this over here for us to have a look at. So in this section here, week 4, I assume that you've all caught up a little bit. Everything that's in here is very, very interesting. Okay, so having said that, you'll notice that the way that differentiation is set is very high school in its kind of thing. And then we've got the chain rule. Now for me, this is the headliner. Okay, being able to do your maths here at this course, you need to be able to do this. And I like the way everything's laid out, showing you the chains and showing you how it's all rebuilt. So if your working looks like that, you're doing well. Okay. The other thing, and it's interesting that as soon as we get off that, we go to implicit, and all of a sudden there's a change to what? Differentiation of expressions. So we move from differentiations of equations, as shown here, particularly in this part, of equations, to differentiation of expressions. And this really, for me, in this section this week, should be the actual emphasis. Okay, this is a simple example, but it's got some great uses for problem solving and other things. So I'll pull it out here, and we'll get that going from here. Alright, so in terms of what I wanted to do, it was just to go and capitalize on the idea that we've got quite a few things that come up when we do an exercise like this. And the exercise like this is y is equal to sine to the -1 x on a. Okay, and we're asked for d dx. Okay, the d dx of this. So the first step there would be to undo. So we would take the sine of both sides, and we would see that that is undo, and so we're left with sine y equals x on a. The next thing we would do is we would d dx this. We would d dx the whole thing. I'm going to use that again, so I'm just going to leave it up there unchanged, and d dx all of this would be read like that. So then we go ahead and d dx the terms, and I'll do a word problem at some point for you, and d dx x on a. So that's like 6x, it's just 1 on 6x. Okay, and so then we've got the d dx of sine doesn't make any sense, so we invoke the chain rule. So what would be the thing that would make sense here? What would make sense here? Because we've got a y function, so we would want a d dy sine y. We would want to make the with respect to variables the same. So this means we get dy dx up here. So dy dx is the thing we're actually looking for when we were asked this question. Another way of interpreting that is in equation form. So I started off in expression form for the differential, and then I end up with equation form, and there it is, it's a rise. So we just got to keep that in mind. And then the ddx of this is just 1 on a. So we can go ahead now and do dy of sine, and dy of sine is cos y, keeping our dy dx. And so we can divide both sides by cos y. And so we'll get a cancel there, and we end up getting the dy dx that we want. Now the issue is that although strictly speaking that's correct, it's not complete because it's not with respect to x. It's got the y form in. So the implicit differentiation has taken place, which is good, and then all we've got to do is go back and do our exact values trick. So we go back up here and we pull this guy like this, and we've got a y and an x and a 1, and we do our associations. X is cos, and I'm deliberately leaving the variable out because I can put whatever in there, okay, because we don't want to get confused over our x's and y's. If we square this whole thing, we will get sine squared y equals x on a squared, which will be sine squared y equals x squared on a squared using your algebra rules. So that might be handy in a minute. Okay, so down here we've got a need for cos, and all we've got at this point is this guy. So we're going to isolate cos squared, theta it would normally be, and we do that by subtracting sine to both sides. And so we get 1 minus sine squared both sides. And finally we want cos, so we're going to take the square root of both sides. And so what we'll get is, and we're only going to take the positive for the sine, so we'll get cos something there is equal to the square root of 1 minus sine squared something there. And of course the thing we're after is y, so it would seem reasonable to put y back in here now. And not only that, we have a substitution for this. So cos y is going to go one more step, and we're going to get 1 minus x squared on a squared. Now we're cooking. Okay, now we're cooking. So what we're going to do is we're going to pull that cos y out of this quotient and put this whole square root of 1 minus x squared. So if you can do this skill, you're there, baby. As a scientist and an engineer, you're there. This is it. Okay, so variations of this, you might want to try x on a. Now you can put this into your technology, and your technology will do the same thing. Okay, so the technology will help you get that out as well. So I'm going to substitute the cos y, and then we've just got basically some algebra to do. And yes, it is a bit tricky, the algebra that's there. Okay, so the thing is with this next, how do we reconcile the a across that? That's annoying. In reality, what we need is we need to go to a transform where we've got this. So how do we get that into that form? Well, it's just the result. So if we, it's the result of undo. If you think of that as the result of undo. So this is where your math starts to kick in now, okay? So what's the undo? Well, the undo would be a squared. Okay. So now what we're able to do is recognize the result of undo, okay? The result of undo, oh, that's a D. I don't know why I changed that. Result of undo is the square root of a squared. So that a is going to become the square root of a squared. So this is just some algebra that you should have picked up by now. That allows us, now that we've got square roots together to put them together. Okay, so it doesn't matter if it's an expression, we can do together like that. So this is the nuance, right? This is what's expected, the nuance is feeding in. So then we'll do that now. We'll do a squared bracket 1 minus x squared over a squared bracket and put that all under the square root. So we've done the step. We did this step, okay, we did the intermediate step, we got them split and joined up. Okay, so isn't maths fun? Awesome. Alright, so then we've got to just do the expansion. So if we expand, we'll get a squared, take the brackets away now, a squared x squared over a squared. So this is a long way teacher happening. And then we've got the square root of a squared, and they'll cancel of course, and so minus x squared. So the d dx of sine to the minus 1 x on a is this guy. Okay, that's the result that we're interested in. And from your tables of integrations, you know that if you get an integration in this form, that it is now okay, and that's the link. That's the reason I do it, to show you how it all goes together. Okay, that's to show you how it all goes together. So what I'll do is just draw your attention now at this critical moment to your available resources. So the Maths Study Centre website, which you all go, oh no, not that thing again, you were the bloke that did the maths, what was it? MRS. I hate that bloke. Well, that's me. So if you hate me, too bad. EDU I want. Okay, and then you do that. You made me go back, and no W's, we just get rid of the W's. It doesn't like W's on our system. So if you get rid of the W's, it comes here. Now under resources, library, we've got modelling, worked examples. You can see the chain up here, so you don't need to write me saying where are they. And chain rule worked examples. Implicit related rates in worked examples. And there's some other integrations and DEs and stuff there. But for our purposes, just some basic old, how do you do differentiation? You do your pre-work, you get them into line. You do your differentiation, pre-work, get them into line, pre-work. Change of pronumerals always throws students, so that's why they're there. Okay, that one's an ugly one because it's dividing fractions. Doing your pre-work, then going ahead and doing it. So we had to do a lot of pre-work. So sometimes the algebra is quite involved when you get to doing that level of work, but it's nothing like what you just did in terms of boom, 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 and implicit, and all the stuff that went together with the implicit. Okay, so please practice those because I think it will serve you well in the future. Now, implicit differentiation. So this is what Mary did. It's just not as good a quality as what Mary did. It's just a handwritten note about how to do it. But here I've emphasized it differently, the DDX, all of it. So this is where I'm emphasizing doing the differential with respect to every term. DDX, yep, 2x, tick. DDX y squared, oops, how's that work? So here we have to invoke the chain rule. DDX of a constant, 25, the gradient is 0. So this is where we arrive. So we invoke the chain rule. What's a good DD for this y2? It's dy dt. So this is all the line by line working of what I showed you earlier in your notes. Okay, where it said this one. So that was this one. Okay, so that's me taking you through step by step and doing all the diagrams to get you to a similar kind of thing. And again, it's important if you do it for that kind of problem, which we'll do. I'll do one more problem and then I'll start taking your requests. Alright, so you do that. Now, the reason this is important, and then you get the same result. So is there any questions about this example and where you got it from? You're all good with that? You can navigate yourself there and get the example and have a look at it. Okay, line by line, it's got the long way stuff. And you notice that's quite different. As exemplar as this is, and it's really good. They are different, aren't they? Do you see the problem, guys? This is the whole point of know-how, right? It's not that one is better than the other. It's just that they have different emphasis. So this is what it's like when you're a student of sciences and engineering. You can read a textbook, but your eyes can spin in your head like the dials on a poker machine. Okay, it's not until you sit down and start to nut through line by line what's going on that your scholarly intent starts to reveal where you're headed in your life in terms of your maths. Okay, so be patient. Like, you know, it takes a lot. I do it very quickly here with you now, but it takes a lot to learn this and to fix it up. So here's a more complicated example. This has got a nasty product rule in it. So this is a nasty example. For the x cubed, here we go, ddxing the whole expression, but then expression term by expression term. So x cubed, very easy, 3x squared. Y cubed, oops, invoke the chain rule, dy dx, that's the dy dx we were asked to find, and then we've got to do the y cubed. That now makes sense, 3y squared. But this up here is nasty, it's got a product rule. So that product rule needs to be worked out. So ddx 6xy, so if it's alright with you, I'm just going to do the right hand side there. So ddx 6xy, and you're doing it explicitly. So this is a product rule engagement. Because why is it a product rule engagement? Because you're going to ddx the y term. You might say y product rule, because there's not, you know, with a product rule, your training says look for two terms multiplied together. That's a product rule, isn't it? That's a lay down Mézières. Here you've got two terms. What? But the difference is it's implicit. Because it's implicit, we now have to do the differential on the y term. See that difference? Your training up to now has been there, but now we're saying, well, hang on a minute, this product rule is going to have a ddx component of its own. In other words, we're going to do the y term with respect to x. Okay, so if I assign the u and v the way we'd normally do it, now isn't that counterintuitive? It's counterintuitive to do the product rule, because this is what your training taught you, to look for two timeses. Well, this is a times also, but it's implicit, so that's a bother. Okay, so our total is going to be u dv plus v du. That's what we're looking to do. So if u is equal to 6x, u dash is very straightforward. V is equal to y. Remember what you're doing when you find v dash is you're ddxing y. It's implicit. Now I've written that down for you. You have to write that down. Alright, so even a simple algebraic one like this can get a little bit complicated. Okay, so this is now, what are we doing? We're not doing this, doesn't make any sense. So what we're going to do is invoke the chain rule. What can we put in the chain that will make sense? Invoke the chain rule. This is why the chain rule is so important. You can't survive, I've said that before, without it. So what's the one? Well, it's d dy, isn't it? d dy of y will make sense, and then we get this dy dx for this term here. Okay, now some lecturers don't write that out in Leibniz notation, they just call it y dash. But you've got to be careful doing that, because that implies you understand that that's a ddx implicit of whatever you did. So you've got to be a little bit careful using these dashes. Okay, Leibniz notation for me whenever the chain rule is on. So the d dy of y is just going to be 1 and dy dx. Okay, so that's our v dash. Our v dash is dy dx, and that's the one that we wanted. That's the one that we wanted. So we've now got to build up our business here. So u is 6x, v dash is dy dx, and v was y, and u dash was 6. I'll just put that there to make that kind of make sense. Okay. Alright, so this is the right hand side. Now, whatever's going on over on the left hand side can now be incorporated in this. Okay, so over here, so we got to this point here, that's exactly the same as the one that I did. So the difference here now is that it's got a left hand side and there's two dy dx's, so they're going to have to be grouped by the plus signs. So that's why I'm subtracting the whole term, 6 dy dx, both sides, so that down here the dy dx's are now common. So this is kind of algebraic steroids, isn't it? Okay, so what we've managed to do is to get the terms with the dy dx's on one side. We've now moved the 3x squared over the other side, so that's there. But look at this, we've got this lovely big plus sign, and we've got two things that are common. An algebra train of thought is what's common. So you can take that out the front and put your brackets in, and whatever's left over sits in the middle there. So to dy dx, all you've got to do is divide both sides by that. There it is, cancelling for a 1, and so you get your dy dx in common, and you end up being able to do that. So I would encourage you, it looks quite different when you do all the lines, isn't it? When you do all the lines, and this is why students struggle with this kind of maths. I don't think it's because students aren't smart. They are smart. Well, the university thinks so, they're going to make you a scientist or an engineer. But I think what happens is just a little bit unprepared to see all the working. It's a bit in your face when you do it line by line, isn't it? It's a bit in your face when all the lines are there. Okay, so any problem that you have that you're addressing, like a related rates problem, will need the level of attention. Okay, so there's a couple of questions there that you can have a look at. Okay, and so they go through and assign the related rates by using implicit differentiation. Okay, so that's why implicit is important. You can't do related rates without it. Okay, so the 10 questions are a popular one that comes up, and then in these word questions what you have to do is pick out the rates. So in the question it says an upright tank with a radius of 5 is being filled with water at a rate of 3. Now often a student that's not practiced in doing these will just let that roll by them, like a, you know. But what we want to do is pick up on the language. So we're being given one element of our chain rule. That's how I'd like you to think of it, please. The words are telling us an element of the chain rule. So one element of the chain rule is given, okay, in terms of meters cubed, which is volume, and minutes, which is time. So what's the rate this one is referring to? How would I express that rate? Volume, minutes, so that rate represents, see, now I've made you think of it differently. Even though the answer's on the page written elsewhere in front of you, your minds are still processing what the hell. Okay, so a rate of 3 volumes, because it's cubes, so it's volumes, meters cubes, and minute is time, so we've got dv dt is equal to 3. So we got that just from the language, and I put it over here. Okay, so that's the hard part of these word questions, just translating the word rates. Okay, and then it's asking how fast. Well, that's a rate. Fast means per time, doesn't it? So that guy there is a reference to a rate. Okay, and the rate reference is to its height. So it wants the height. So there's the word thing kicking in again. If you're not well practiced at this is the puzzle. Height for time. We want DHDT. We've got dVdt, DHDT. We don't need anything else in a way. What we can do is, if I just go away and be a bit rude and just say dVdt, I'll come back to that page. We know we've got a dVdt, and we know we've got a DHDT. So how do I relate those for a chain rule? So this is about expectation now. How would you put them together? Okay, how would you put them together? So you can just play with it. Well, we were told this was equal to something. So it looks like the chain rule's over here. So what do you think the chain rule would look like? Like that, wouldn't it? So what we have is maybe a DH on the bottom. We don't know anything else about the question, so what would go on the top here? We're still going to get dVdt.
Just D, or would it be
dV.
dV?
Yeah. So dV. We're still going to get dVdt. There it is there. It's just that we're going to go through something else to get it. Okay, so when we look at that as a left-hand side and a right-hand side, it looks a bit weird because that looks like a definition, doesn't it? That's like saying, but it's actually, this has got a value. We've been given a value, and we've got some bits missing that we have to fill in for. So once you get the hang of using the chain rule from the words, you're masters. You'll be masters at this. So it'll take a little practice, but please bring it here if you need help with it, or send me an email or something, and we can work through it. So these are a great way to get used to that. So in this case here, we know the volume of a cylinder is the circle times the height, but this is the volume in terms of radius and height. It's not V in terms of T, V dt. It's not this one, it's not V in terms of T, so we're short. That's not an answer, it's just a stop gap. But if we do d dt of this, you say to me, well, where's the T? Well, we don't need the T. What's this represent? This represents implicit differentiation. Okay, implicit differentiation. We get told the radius, I think in the question, the radius is 5. So when we put the radius as a number, that gets to be a number, and we're left with V in terms of H. So if we're going to do V dt, V in terms of H, this you have to recognise is implicit. There it is there. It's an implicit. Oh. Okay, so the first few times you do these, you might struggle to put together the chains, and you might struggle to put together what information is telling us it's implicit. Because, you know, you wouldn't do it. You wouldn't, just having been introduced to implicit and picked V equals 20 pi 25h, you wouldn't have turned around and said to yourself, oh yeah, that's an implicit. You wouldn't have done it. Okay, but now it's being pointed out to you that it is implicitly, then we'll do a DDT for both sides. So a DDT for that one and a DDT for that one. So a DDT for that one gives us dVdt, that's what we wanted. A DDT for this term here is going to be 25 came down, 25 came down, so it's going to be in terms of H. Now DDTH, put the constant out the front, doesn't make any sense. Okay, but it does when you invoke the chain rule. Okay, invoke chain rule. So here now we've got our H. What's the best thing we can do? DDH. So this now makes perfect sense. It aligns with our understanding of differentiation, and we got the DHDT that fits in the chain rule. So that's just one. So we get 25 plus this one here. Okay, so DHDT we can move it around to give ourselves a thing, and then what we're going to do is put it back into our chain rule. Oh, that was actually the question. How fast is the height? So how fast is the height? That's the number that tells us how fast that height is, changing with time. Okay. So the invocation of the chain rule, when the missing pronumerals, I'm stuck, I can't go any further. Yes, you can. Implicit it. Implicit it. That's the trick, isn't it? That's the little trick. Okay, so when you get your word problems, you've got a bit of work to do to get them all pumping away. So be careful with your practice and your practice skills and stuff and your tutes. Make sure you work them to the level of detail that's provided here. Okay? Alright, any questions about that so far? All good? Alright, so there's a couple of other examples there that are worth looking through. Same kind of thing. When you get the clue, what's the rate? That's something. Sorry, that's something. And so what is that one? That's area time. So that rate represents d/dt. I think, without going into it too fast, that would be d/dt. This one doesn't want the area, it wants the diameter decreasing at a particular time. There's the clue word. Okay, so this one here is d/dt, and it's equal to 5. Okay. So the area of a sphere, and so we go ahead and do all of that, and so you get it in terms of diameter. We want dA dt. We've got the number for dA dt. We know that's 5, but we want the rest of it. Okay, we want the rest of it. So how do we do with respect to t for that one? Well, the answer is implicit and invoke chain rule. Okay, and before you know it, you'll be whizzing through the problem. So we d/dt both sides. We've got our dA/dt. We know that's a number, was given to us. But then we've got d/dt pi squared. We invoke the chain rule. We've now got it making perfect sense. d/d, d squared, bit odd, but we got the differential. Okay, and that's the bit that we wanted. So then you just go ahead and rearrange it, and you end up with the diameter time. Okay, diameter time, which is what the question was asking. Diameter decreasing when the diameter is 8. I think the substitution for the diameter was made at that point. And the 5 was put in, was decreasing, so we had to make it negative. That was the only clue you got about that. Diameter decreases, we said it was 5, but we want it to be negative, so it's got to be decreasing, -5. Okay, so watch out for that kind of thing, it can happen. Alright, so there's a few examples there for you to look through, and once you get the hang of them, what you'll find is that it's fairly straightforward. Okay, so what I'm going to do is pause there, because that's been a lot. And okay, now we get back to, that's what Jason wanted to do this morning. Alright, I think that fits with what you guys have been doing. What do you need me to do?
We've actually, this week's test is still on the cross product, and the tutes are on matrices. So maybe if we could start with a couple of examples of sort of the harder cross product questions, and then go into run through some matrices, that'd be good.
Okay, alright, so with the cross product, what's the cross product doing? I asked you what the dot product was doing. What does it do? So see if we can remember that. So the dot product told us the degree of pointing in the same direction. Okay, it was a number. Okay, and some extreme examples. the dot product of these two would be what?
0.
Right. So then so on and so forth. Okay. What does the cross product do? So the cross product gives us a normal. I'm just telling you. A normal to the plane formed by the vectors. Okay, so it gives us a normal to the plane. So in that way, the dot product is a little bit easier than the other ideas that you're using with matrices. So if I have A equals I plus 2j minus 3k, and then I had B equals 4i plus y plus 2j plus 2k, something like that, ijk, I would immediately change them to their component form, but that's just me. Alright, I would immediately change them to their component form. That's how I would deal with them. Okay. Now, when you do the dot product, the cross product of A and B, the order is very important. And there's two things that you get to see. One of them is the vertical bars. The vertical bars tell us in matrix, no matter what, that you're going to be doing a determinant. So that has a special form, a determinant. Okay? And the way that that will work is that the order is important because A is going to go in the middle row and B is going to go on the bottom row. Okay? And up the top is going to go I, J, and K. Okay? So that's what'll sit. So what we'll do is populate those. So just to emphasize that, I'll just change the color. So we've got 1, 2, minus 3, 4, 1, 2. Okay, so that's just to emphasize the way that you do that. Now, the way that we do the determinant, how do we do a determinant? Well, what we do is we're going to do it 3 times, so I've got to make sure I fit it in. So what we do is I, J, so sorry for rewriting it all the time, but I'm trying to emphasize something here. So what we're going to do is we're going to go to I. We're going to take the I address out, and before we do that, we're going to check it. Okay, we're going to check it, and it's going to be row 1. The address is this. This will come up useful for matrices anyway later. Is 1 row equals 1, column equals 1. It's always row column, or if you like, 1 1. When we come to do the little check on the way to putting the I out the front, we do minus 1 to the power 1 plus 1. And they came from here. That 1 was there. And I don't know if Mary's done this, but I'm doing it. 1 plus 1. So then what we get is we get I out the front. Now, what's the result of this? The result of this is minus 1 squared. Anytime there's a minus 1 squared, it's just going to be 1. So I'll put it in there just to be annoying, but it's minus 1 times I, plus 1 times I. And then our submatrix for I. Okay? So what we're going to do is then go 2 times 2. Put your brackets in so you don't spoil the minuses. Minus 1 times 3. Okay, and so that's minus 3, 4. 4 minus minus 3 is 4 plus 3. So that one is 7. So we get 7i. And I'm just going to put a big plus sign because we're going to plus it to what comes next. Okay, the next thing is we've got I, J, K, 1, 2, minus 3, 4, 1, 2. And what we're going to do is take the middle, because the determinant means we're just going across the row. Okay, that's what the determinant means. Across a row or down a column. Now, why do you choose which is which? For your convenience. Whatever suits you. So that's I now, so we're going to go down the column here and wipe out the column. So that's our submatrix. So we've got, now we're going to take J and go on that journey again. Minus 1. Now what's the address of J? Row column. So it's 1, 2, 1 plus 2. So it's minus 1 to the power 3. That's an odd. I made the point before, if it's an even, it's a square, it's a positive. So we're going to get minus 1. So down here we're going to write minus 1 times J submatrix. 1 minus 3, 4, 2. Okay, and then what we'll do is we'll put 1 times 2 minus 4 times minus 3. Now this business of putting the brackets in, it's not just Jason being the long way teacher, it's really highly recommended. Okay, because if you don't, you're going to get confused. Minus 4 3s are 12. So 2 minus minus is 2 plus 12. So minus J14. So in actual fact, it becomes a minus. So I'll do them all down the row. Okay, the final one. The final one, I'll put it here, is I, J, K, so this time we're going across the row, but this time we're going down K. We go on our journey. Row 1, column 3. That's an even. So this is a 1. We won't even bother with that. So we're just going to put K. And our submatrix is 1, 2, 4, 1. Okay, so we get K outside of 1 times 1 minus, I know, you're thinking, gosh, you're a goose, you could have just done it in your head. 1 minus 8 is minus 7K. So the total matrix result is, let me go back to the blue, 7i minus 14j minus 7k. That will be orthogonal to the plane formed by those two. Okay? Orthogonal just means normal. Okay, so I can't sketch it quickly enough to make it pretty. I probably could try, but does everybody understand what's happened there? Okay, so we've got this wonderful plane. Okay, and if I just do the result. I'll just do the result. 7 minus 14 way down here, minus 7 way down here. So there's some plane, it's orthogonal to the plane. I won't bother with it. I shouldn't have done that. I should have just left it. You can do it on technology, but it'll take me a couple of hours to do. Alright, is that good enough for those?
Yep. Yep.
Is that the kind of thing you wanted?
And maybe, let me just go, hold on, I'll pull up the sheet and I might be able to ask a specific question.
So is it from the tutorial practice tests? What?
From the tutorial.
So tutorial 2, is it?
Yeah, that's it.
Yeah. Okay. So what would you like?
Let me just. The projectile motion and vector functions. So some of the longer word questions start with it's in modeling C section and probably working through A.
Is this the tank fires?
Yes, that's correct. Yeah.
Okay. All right. All right. So now, I guess one of the things about this is it's using parameters. So do we get the parameter idea? I guess that's my question. All right, let's just do it and see what comes out. And if I need to go backtrack, I will. All right, so if a shell follows the path defined R in terms of a parameter, but that's also a vector. How do I know it's a vector? Because it's got this underneath it. And it's being made up of parameters. T will change the location. Cos alpha, that's a unit vector, plus TVO. So it's got the components. 4.9. Sine refers to y. Y is going to be gravity, isn't it? So that's why we've got 4.9 t squared j. Okay, so it's telling me t is the flight in seconds. I'll just get that. Sorry. T is the flight time of the shell in seconds. VO is the speed in meters per second at which the shell exits the barrel, and alpha is the angle at which the shell leaves the barrel in radians. The shell is fired across a flat expanse at a symmetrical mount with a width and a height of 1,000. The base of the mountain is 12,500. If the shell has an initial speed of 500, at what angle must the shell be fired so that it's exactly at the base of the mountain? With what is its time? So if the mountain's like a pyramid, is that the way you looked at it? I don't know, is that how you thought of the mountain?
Yeah.
And so the cannon and the base of the mountain would be like that. Is that the idea? Okay, so we've got to put together some coordinates for our system. These things won't work without a coordinate system. So what's the base coordinate for x and y? So x and y, it's 12,500. Is that what it said? The base of the mountain is 12,500 from the tank. Okay, so that's a coordinate. And because it's landing on the same ground as the tank, the y coordinate will be 0. So again, it's a word problem. That's hard to pick. Okay, so the target is 3D. And it's actually x and y, so it's going to be like that. And that's the base of the mountain. and that's the tank. Something like that. I don't know how helpful that is, but anyway. So for the first one, for this component here, we've got 12,500 is equal to 500 T, so that's that bit. Now we're doing the T, and then cos alpha. For the second bit, that's 0. 0 is equal to 500 T sine alpha minus 4.9 squared T. This can be rearranged for T easily in that T will be divided by 12,125 over 5 is 25. Okay, so we've got a couple of equations there to help us. Okay, now can we put T into that one? We substitute it into there and there. Yep. So we'll have 25 times 500. We're back to 12,500. 25 times 500 is 12,500. So that came back purely as coincidence. Okay. T was cos alpha. On the bottom. So we already had a sine alpha. And we're bringing the cos alpha in. So y over x, so that's tan, if need be. Minus 4.9 squared times 25. Does somebody want to tell me what that is? 4.9 times
You might have put 49 rather than 4.9.
Yeah, it's 4.9.
Didn't look right. I know you love it when I do mistakes. Is that right? Is that better?
Yeah, I think that's, yeah.
No, no, I did the square root. Let's try one more time. Squared. There's something not right there. Now what's happened? 4.9 T squared. Okay, so the squaring's not on the 4.9, it's on the T. So that means 25 squared. Whoops. Alright, let's try it again. 4.9 times 25 squared. That's more like it. I think that's the one we wanted. Okay. So that makes it a bit easier. So we've got 30625. And because T, so we've got cos squared on the bottom. Whew, gee, that's a lot of work. That's a lot of work. Alright, so we've got this version here. What are we going to do with this? We're going to clear fractions. How do we clear fractions? Come on, basic algebra. You times by the highest product on the denominator. So we're going to multiply by cos squared alpha. So we've got 0 times cos squared alpha 12,500 cos squared alpha so we can see they will cancel. One of these will cancel, and that's still 0. So we get 0, a cosine product, okay. Now, this is a problem here in trig, because we've got the problem of how do we get this in terms of either sine or cos. Okay, so we've got to go and find an identity that'll help us do that. So it's one of the a plus b's. Now I'm just thinking what happens when we do sine A. That's it, isn't it? That'll give us the product that we want. That'll give us the product, because it'll be 2 sine A cos B. Is that right?
Yes, sine A cos A.
Yeah. So that's the one we want. So sorry, a little bit of fiddling there because I don't know that off the top of my head, but that's the one we want. We in fact we just want that bit. So that's the bit we're going to substitute. So we're going to put in 12,500, and we would have to multiply by 2. So we would have to put 2 lots in. Let me get that right first. Okay, so it's going to be 2 lots. Okay, so we would halve it. We would have to have the half. So what's half of 12,500? That's annoying. That's really annoying, because what it means is you would have to divide by 2 both sides. Okay, and so what you're actually putting in is a half sine 2 alpha. That's actually what you're putting in. So your 12,500 is going to get halved, and then you'll put in sine 2 alpha. Okay, so that's a little bit annoying, to say the least. That's a hard one. Okay, so half of 12.5. $6,250. Alright, so we've got it down in terms of alpha and sine. So you just rearrange all of that. So add the 3062 to the other side, divide it by 62, so I'll leave that for you to figure out, but the double angle will be Okay. Now, how are we going to get to the 2 alpha? So 2 alpha, and then alpha will finally be divided by 2. I'll let you work that out. Okay, so I think that one will give you alpha, and then t is just using that cos in one of the other equations. So I'll let you work t out. Does that help?
Yeah, that helps. Yep.
Yeah, so there's a little bit of trickery there. This is hard. This is a hard translation to understand the problem. Okay, that's a hard one to understand the problem.
So is this type of problem just we kind of translate the problem into a coordinate system and use that system to solve this kind of thing?
Yeah, we haven't quite got to translation of coordinate systems in your course. You do that more in math too, but yeah, the words to, it's just demonstrating the understanding of the question, because you were given this initially, and then if you like interpreting that in terms of this, I suppose that it's just that you use the word that means something else. So when you move between coordinate systems, that's a thing, and you'll learn that in mathematics too. So Cartesian to polar, for example, in this particular case, it's just interpretation, I feel, is a better way of expressing what you're saying. Yeah? I don't know what you think about that, but it feels like interpreting the question and getting it on to the 3D coordinate system, which is what you said.
Yeah, that's what I mean. Yeah,
Yeah,
I
yeah.
understand.
No, that's all right. I'm just making you aware that it means something too. all the words start to mean things now. when you do your maths, all your words mean things. Yeah. So the hard part there is the setup. That's a hard question, I must say. All right. So you can do the t. You can pick one of your equations and solve for t. You've got alpha. So probably this one here you could solve for t to get your time of flight. Okay. So that would be okay. Alright. Yeah, a bit tricky. That's annoying. That's annoying having to see the double angle. Alright. Was that as much as you wanted to do there?
Yeah, that covers everything for me. I'm not sure about the others, but yeah.
Okay, that's good. Alright, now, you were asking, and this is something else from someone else, you were asking about matrices and an intro to matrices, yeah? Okay.
Yeah, yeah. So I understand the basics, but if you just want to, yeah, go through. I got a bit lost in the lecture in the last couple of episodes, like the last 40 minutes or so of the lecture.
Okay. And
Just when
what
it
was...
came to the ADJ, adjunction or whatever.
Oh, yeah.
Yeah,
Okay, I get it. Alright, so there's a couple... Okay, so this is about invertibility. Alright, so there's two main sections that we need to be aware of. There's matrix. Matrix matters, and the sheets they've got, the book they've got is really good. And then there's determinants. Now determinants we need to be careful because the rules are different. The rules between the two are different. Okay, so there's some rules you can do in determinants that are different to the matrix rules. So you need to be aware that there's a divider about that. Okay. Now, in terms of an inverse, there's basically three methods. There's your row reductions. There's your cofactor method. and then there's your use of determinants to do that as well. Determinants. Now I'm not sure what they're going to ask you to do in terms of any kind of testing and such, but now I think last week I did do something, didn't I, that showed simultaneous equations, and so I won't repeat that because that was in last week's part. Have you started doing eigenvectors and eigenvalues?
Sorry, can you just repeat that?
Eigenvectors and eigenvalues?
As in, like the one.
The matrices?
Yeah. Yeah.
You have started doing that? And did matrices, is it start and finish this week, or is it last week? Or it started and finished last week, didn't it?
Yeah. Well, the thing is though, because the tutorials run behind the lectures, like we have, the lecture was last week, our tutorial on it is this week, and we don't even get tested on it until next week.
Okay.
Yeah.
Okay, so the tutorial, okay, all right. Okay.
So I have my tutorial tomorrow, and tomorrow's tutorial is, like, for me, the first time I'll actually do questions on matrices and stuff.
Oh, I see. Okay.
Yeah.
All right. Okay. No worries. All right. All right. So there's a couple of there's a couple of things about matrices that we need to be aware of. All right. So let's do a simple one. Let's do a simple one. And something like this. I'm not sure where they'll meet exactly. So the way that we would put them together just moving them over the other side. Now we would augment this. So it starts off with an augmented, it always starts off with the coefficients. Okay. Now, in terms of, because we know this comes from a linear set, we can solve it. So the basic idea is that you always start with a target, and the target that you're looking for is this one, and you're looking to make that a 0. Okay, so if I do row 2 becomes row 2 minus row 1, I'll get 1 take away 1, minus 2 take away 1, and minus 7 take away 3. So I'll change the first row, the second row, to minus 3, minus 10. Now this can be reinterpreted as minus 3x is equal to minus 10. So then we can rebuild it, if you like. Divide by minus 3. X is equal to 10 on 3, which is 3 1/3. So that point there is 3 1/3. So that's one of the solutions. I can then go and substitute that back in and say y minus 2 lots of 10 on 3 is equal to minus 7. So rebuilding that again. Okay, rebuilding that again from the first line. Okay, so in that case there, we'd get minus 20 on 3 equals to minus 7. So we'd add it to both sides. So y would be equal to minus 7 plus 20 on 3, which would be 3 7 to 21. So minus 20, so it's a negative a third. So it's just below there. So that would be your y value. So that's a fundamental skill, being able to get to that point there. Now you're not going to be tested on doing that, I don't think. Okay, I think all that does is say, oh, okay, so this is how we get the x and y variables out. The next thing that you would be asked to do would be to make this a 1. So we had a diagonals of 1, and then make that a 0. So in order to make that a 1, row 2 would become row 2 divided by negative 3. So we won't change the top one. 0 divided by negative 3 is still 0. Negative 3 divided by negative 3 will become a 1. And negative 10 will become negative 10 divided by negative 3, which is 10 on 3. So that's our x column that we can read off directly. Rebuilding that, x is equal to 3 1/3. Well, we got that when we did the back substitution, the rebuild and the back substitution. We didn't. Here we had to do a calculation, a rebuild. Here we're just reading it off directly because of the 1x. Oh, x is 3 1/3. It comes to be the same thing. Okay. The next thing we want to do is target this guy and make that a 0. So there's a pattern. There's a pattern to what you attack, and it's true when you do row reductions in matrices, and I'll get to that. Okay. So what we'll do here, we do row 1 is going to become row 1. What are we going to do? We're going to add 2 times row 2 to it. So 2 noughts are naught, 1 plus naught is 1. Okay, 2 ones are 2. 2 minus 2 is 0, we did it. And finally, minus 7 plus 2 lots of 10 on 3. 20 on 3, minus 7, there it is, we're doing the same calculation. Okay, minus 7 plus 20 on 3 is going to be negative 1/3. So we got this matrix now. Now y, we can read it straight off. So the reason that you do the processing of the rows is you get to this final point where you can just read things straight off. Okay. Now, in terms of your operations, that's one of the goals, and being able to manage that is quite scary. Okay. Now I'm approaching this slightly differently before I run into all of these, because I want to do multiplication. Now matrix multiplication is the most important thing you will learn in matrices. So if I do a 2 1 like that, 2 1, as a vector it would be 2 1, a column vector. Okay. Now what I want to do is I want to multiply 2 1 by some other matrix. Now there are rules about this, and I want my matrix to be changed from a 2 1 to a 1 2. So I want my V to be changed to a U, which equals some transformation metric times V. This is the usage of this. This is very important for eigenvectors. Okay, so what numbers do I need? I need this to be a column vector 1 2. So I want the result of my multiplication to be 1 2. So I'm doing it backwards for you, right? What goes in here that gives me the result? This is really important, people. Okay, this method of multiplication. So I'm going to put in placeholders here, and I'm just going to do A B, C, D. Now, to do a multiplication, it's row down column, sum of products. And we're familiar with that because we did that for the dot product. So you need that phrasing in your head. So we're going to go row down column. So we're going to go A times 2 plus B times 1. And that will give us this first one. Okay? So what would be a good A and a good B to give me the number 1? Row down column is going to give me the number 1. Well, I'd like to eliminate the 2, so a good version of that would be 0. Keep the 1, a good version of that would be 1. So up here, my first it's going to be 0, 1. Okay, row down column will give me 2 times 0 plus 1 times 1, which will be 1. Alright, row down column is going to be C times 2, sum of products, D times 1. And I want it this time to be 2. So what's a good C and D to use? Let's keep the 2 and let's ditch the 1. So if I put in 1, 0, I will do the transformation of V up to V. Multiplication by matrices is what you would have seen in your lecture notes. This is actually what it's meant for. The whole thing is about transforming a vector. Now I know that you do bigger ones, just as a matter of course, but there's a couple of ideas here that really are important. Okay, and it's this transformation idea that is the most important idea. Okay, you do matrix multiplication because you can do a transformation on a vector. Now, let's think about the problem of doing a multiplication of 2 vectors. I mean, whoopee-doo. I don't mean to be facetious, but row down column. I mean, that's a basic skill. Row down column. What you've got to do for your first placeholder is 1 times 5, sum 2 by 6. So we can do this then row by column. 1 by 7 plus sum of products 2 by 8. So you get this kind of training, right? Row down column. 4 times 5 plus 3 by 6. This is me being the long way teacher again. Row down column. 4 by 7 and 3 by sum 3 by 8. Okay, and so what you get is this thing. Now when you do this, this is all well and good for you know, the exercise of we did a row by column. Oh great, that's what you do when you do the textbook version, but that doesn't tell you about this. No, it just tells you about this. And it also says, well, what are the other circumstances when we can do a row by column and they're different sizes. So the row column has to match. So if we've got a 3, the column can be a 3, because you can do row down column, and you can do row down column for a second one, row down column, and you could keep going that way. I mean, theoretically as many as you wanted, because you're doing row down column, and then the same thing here, row down column. So you'll get however many verticals there are, that's how many sum of products you'll get. Okay, so that mechanism of multiplication, while you learn the structure of how to do the multiplication, that's important, but the message of multiplication is transformation. Okay, so the transformation message comes out a couple of times. Now, one of the places that it comes out is in eigenvectors. Eigenvectors and eigenvalues are simply doing transformations of a particular type. And all it means with an eigenvector, eigenvalue situation, and I won't jump into it too much, but if I've got a vector V and I do the eigenvalues and eigenvectors for that particular vector, that is the theoretical stretching of the vector, shrinking of the vector, reversing of the vector, and any number of ideas. But what it's doing here, it's staying on the dotted line. Okay, and this is a special type of transformation that occurs when you do eigenvectors and eigenvalues. So you do eigenvectors and their corresponding eigenvalues. Okay. Now this theoretical thing here is called the span of the vector, and provided it doesn't get knocked off the span, then you have the result of eigenvectors and eigenvalues. That's all it is. But it always translates into you doing some kind of multiplication matrix. Okay, and all of that little fiddly stuff at the end that you do when you do your eigenvectors, eigenvalues, results in an increase or a decrease, a squishiness or a change in direction, but not knocked off the span. Whereas this one's knocked off its span. This one's completely off its span. So it's not an eigenvector, eigenvalue situation for this basis. For this basis, this is where you go to in this subject. Okay? Now, in order to get to that point, there's a number of things that need to be done in preparation for that. So in a way, I feel like I've got to pause there because I've skipped this bit. Okay, finding the inverse. All right, does that help in terms of the basic ideas?
Yep.
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 Okay, so now to find an inverse, there's a couple of different, we've got these methods that we use to find inverses, and I'm going to tell you straight up, the way that it's presented in the text, in the lecture notes, as a book that you read, on one level it's beautiful, but on another level it doesn't convey to you the absolute head-banging frustration you're going to experience doing it. Okay, so when you do inverses using any of these methods, you're going to feel like you're having your teeth pulled. Okay, it's just the way it is. So once we move away from the basic questions of how to do multiplication, adding, subtracting, all that kind of stuff, then we get to how do we generate an inverse, and that raises another important aspect of what you're learning about matrices, and that is matrix algebra. So in matrix algebra, it's like a high level matrix algebra presents itself almost like what we talked about with implicit. Oh, you've got to do implicit, have you? Okay, so what I'm going to do here, yeah, I'm just going to